Okay, YouTube, in this video we're going to introduce the concept of a polynomial inequality. And so to do so, what I'd like to do is start by considering polynomial equations and talk about how we find their solutions, and then maybe interpret what we mean by a polynomial inequality. So let's go ahead and start by considering this equation that I've left us here. And this equation here, x squared minus 4 equals 0. I suppose I do want to start with what the solutions are and where they occur graphically. And so what I've provided here is just a graph of x squared minus 4. You can see that this is just a parabola shifted down 4. It goes right 1 up 1. But goes through these two zeros that we see listed here at positive 2 and negative 2. And certainly algebraically, if we were going to solve this, we could solve using square roots just by adding the 4 to the other side here and just taking the square root. We say the square root of 4 is plus or minus 2. So with respect to the solutions here, what we're looking for are all of the x values that cause the left side of this specifically to be equal to 0. But what I want to consider is this, that the left side here is really, okay, some function of x that we have graphed here. And so what we're looking for are what are the x values that cause our graph to be specifically, explicitly on the x-axis. And so we get plus or minus 2. What I do want to consider, though, is the inequality now x squared minus 4 is greater than 0. And so when we talk about this here, x squared minus 4 is greater than 0, again, what I want to recognize is that this expression here on the left is really just some function of x. And so another way to interpret this is we're saying for which values of x is our y value going to be positive on our graph. And so looking at this question here, I do ask it again. We say for what values of x is x squared minus 4 greater than 0 or positive, and where does this occur on the graph? And so as we go look at the graph here, I want to know just what are the x values that cause my y values to be positive. So where are the positive y values on our graph? Well, we know that looking at this graph here, any positive y values would have to lie above the x-axis. And so we could see that, you know, if I were to color in my graph from here to here and here to here, we could see that all of these y values are positive. In other words, these are the areas where our graph is greater than or equal to 0 for its y values. And so we say, where does this occur? The interesting thing is what we're looking for, though, is for what values of x is this positive. So in terms of for what values of x is our function positive, it would be all values of x for which our graph is above the x-axis. And so we say, well, where is the graph above the x-axis? Well, that would be true for all x values that lie to the left of negative 2, 0 here. And it would also be true for all of the x values that are to the right of positive 2, 0 here. So now the question is, well, is our graph greater than 0 if it's on the x-axis? And the thing here is this. If we were at the 0 here, we're at a height of specifically 0 here, then these would not be y values greater than 0, but y values equal to 0. And so we would discount those there, and we would say that, well, then really the x values that we're looking at here that cause our graphs to be greater than 0 would be all of these x values that I've listed here, except for not these two zeros themselves. So in terms of where does this occur on the graph, for all x left of negative 2 and right of 2. So now in terms of how we want to write this, we tend to want to write these in interval notation. So you notice I used open dots here and here because we were saying I only want the x values that cause my function to be only positive, and so it wouldn't happen at the zeros here. In terms of interval notation, though, we tend to write parentheses when we exclude something. And so in terms of interval notation, we would say that the solutions to where this graph would actually be greater than or equal to 0 would be all the x values for which our function is above the x-axis. And those intervals we recognize were from negative infinity to negative 2. But we shouldn't include negative 2 because at negative 2 we're actually at a height of 0 and not greater than 0. And this is in union with, okay, the set from 2 to infinity. So pretty easily on our graph here we can see that these are the x values that cause our function to have positive y values there. Looking at this next question, I ask how would this be different if x squared minus 4 had been greater than or equal to 0? Well, in that particular case we would have said, well, our graph is actually greater than or equal to 0 at these y values, and so in terms of what x values these would be, we would actually include the endpoints here because our graph is not just greater than 0 but greater than or equal to 0 for all x values, okay, on these intervals here, where we would actually include the endpoints because at those endpoints, of course, we know our function's at a height of 0, but that still satisfies this because it's greater than or equal to. So when we see greater than or equal to or less than or equal to, we tend to use brackets on that endpoint. Okay, but if we have greater than or less than, we tend to use parentheses. Okay, so what I want to recognize is that we're basically just looking for the x values that cause our function to be either greater than 0, greater than or equal to 0, less than 0, or less than or equal to 0. But in terms of what we know about our function, we know that our function, let's consider this question here. We say, where does a function change from positive to negative values or vice versa? And so when we talk about function values, okay, function values are y values. So on this particular graph, basically what we want to point out is that our graph can only go from negative y values to positive y values where it crosses over the x-axis, and then we would have negative again and positive, like something like this here. So if our function only goes from being all negative to all positive, or all positive to all negative, where it crosses the x-axis, then what we basically want to recognize is this. Our function is going to change from either being negative to positive or positive to negative only at the zeros of the function, because these would be the locations at which our function goes from being above the x-axis to below the x-axis or vice versa. So let's go ahead and make sure we list that here. The function values can go from being positive to negative or vice versa only at the zeros of the function. And the fabulous thing is this: between the zeros of the function, okay, like between this here and this here, we could see that our function either has to be all positive on that interval of x values, or between these two zeros here, you could see that it would have to be all negative between those two x values. So with respect to finding the solutions for polynomial equations, what we're really doing is looking for intervals, okay, of x that cause our function to be above or below the x-axis, but we know that they can only occur at zeros. So what this is going to do for us is it's going to present a way that we could solve polynomial inequalities more formally. Okay, so let's go ahead and take a look at these steps that I have here, and I'll walk through some of them with you, and then we'll consider the graph of this and see how that supports us. So we say that our procedure for finding the solutions to polynomial equations, the first thing we want to do is gather all terms of substance to one side of the inequality. So essentially, if I were to have something like this, hypothetically, x squared plus 5x is less than 6, I would have to bring the 6 back over to the left side here so that we've established a 0 on one side, because what we're really saying here is that we have some function of x, and I want to know what x values, okay, cause our y values to be, in this case, less than 0. So what we're going to do is we're going to gather all the terms of substance to one side, getting a 0 on the other side, and then we're just going to find the zeros of the function. So let's go ahead and start with this. I've already gathered all my terms to one side. What I'm going to do is find the zeros of this. So I'm actually going to take the time to actually set it equal to 0 and say, what would our zeros be? Now anybody who can factor here knows that this would be a positive 6x minus 1 here, are our two factors. So in terms of the zeros, let's make sure we list these here. We say that our zeros are x equals negative 6 and x equals positive 1. Okay. So what I want to do now is I actually want to set up what we call test intervals. So in terms of my sketch, I'm not actually going to sketch the graph. What I'm going to do is I'm going to sketch the x-axis here. And what we're going to do is we're going to put all of our zeros that we found on the number line. So for instance here I say 1, 2, 3, 4, 5. I'll go 1, 2, 3, 4, negative 5. We'll go negative 6 here. So I'll label these here, 5 and negative 5. But I would say that I have a split at 1. Okay, that's a 0. And I also have a 0 at negative 6 here, and I'm going to label that as well. So with respect to our test intervals, let's go ahead and actually set aside a piece of our paper here where we're going to say that we have test intervals. Okay, so these test intervals, we're going to just set up all of the different intervals that are created on our x-axis by these splits here. So our first interval is actually going to be from negative infinity up to negative 6 here on our number line. Okay. With respect to our next interval, we would say from negative 6 up to the next 0, 1, and then our last test interval is going to be between 1 and 5, oh sorry, not 1 and 5 here, but 1 and infinity, okay, a 1 to the right. So basically you can see that these two zeros split up our number line into 3 subsections, and what we want to know is our function positive or negative in between the zeros here? Because remember that our function has to be either all positive between two zeros or all negative between two zeros. But what we want to do is select test values. Okay, so here's the deal. once we find our zeros and we split up our number line into our test intervals, okay, what we're going to do is choose representative x values within each test interval and test them in the original, and you'll notice that I italicize this here, inequality. And so keeping the intervals for which test is true is going to be what we're looking for here. But basically our original inequality up here, what we're going to do is we're going to pick an x value out of each of these intervals here. So we say out of our first interval here, we would test, say, I don't know, between -6 and -infinity, I might test -7 here. So we'd say we would test -7 and we would evaluate this and see if we get a true or false statement. So what I'm going to do is I'm going to bring my original inequality down here, and actually what I'm going to do is I'm going to write it in this factored form. So I have x plus 6, x minus 1, and we have this is less than 0. So with respect to this, what I want to know is, are all of the x values on this interval from -infinity to -6, are they all positive or are they all negative, okay? And do they satisfy the original inequality? So what we're going to do is we're actually just going to substitute in then to our function here this value of, -7. And so what we're going to see happen here is this. We get -7 plus 6 comes out to be a -1, and -7 minus 1 comes out to be a -8. So what we end up with here is this statement that 9 is less than 0. Now, as a matter of fact, 9 is not less than 0. So what this is going to mean for us is that this test value fails. And I'm going to write a little note here. This fails. And so what that means is our test interval up here, all of our function values are actually greater than 0 on that interval. And we could, actually this is just a parabola that kind of goes up and through here. But you could see that these are all positive y values here. And so in terms of test values, let's choose an x value between -6 and 1. I would say that 0 is probably the easiest choice to test here. So we're going to test now x equals 0. And when we plug in x equals 0, let me do my work over here this time. I get 0 plus 6, 0 minus 1. We're saying less than 0 here. So what I end up with really is 6 times a -1 is less than 0, or -6 is less than 0, which it succeeds or it's true. Okay. So for a true statement here, that would mean that 0, at x equals 0, we have a negative y value. But that would also mean that all y values, given all these x values in this interval here, will be negative on that interval. And so since this is true, I'll put a little box around this. Let me switch my colors here. But this is going to be in the accepted solution interval here. And so we're going to test from 1 to infinity here. I suppose I would test x equals 2. And so plugging this in, we get 2 plus 6, 2 minus 1 is less than 0. In other words, we get 8 times 1 is less than 0, which 8 certainly is not equal to, okay, or less than 0. So this would fail here. This would fail. And since it fails, it means that all of the x values on this interval here would fail. So in terms of solutions, what are we looking at for solutions here? Essentially, what we're going to say is that it's the interval, or all x values from -6 to 1. Now the question here is, should I include the endpoints? And the reason why we should not include the endpoints is simply because, well, this was just less than and not less than or equal to 0. And we know that our function's actually at a height of 0 at these two x values right here. Okay, so to look at this graphically, okay, x squared, let's go put this in, x squared plus 5x minus 6. We could see that our function, okay, is indeed having negative y values for all x values between -6 and 0, but we shouldn't include -6 and 0 because we said less than 0 and not less than or equal to 0. And you can see that clearly here we had positive y values on the outside. And so when we go look at our intervals here, that's why we discounted these two outer intervals and we kept the solution interval here. Okay, so what I want to do is I want to try this again. Okay, looking at this polynomial inequality right here. And we'll just go through our steps as we did in the last one. So the first step is make sure that we get a 0 on one side. And certainly it's easier to put these over here on the left. So we're just going to move these back over. X cubed plus 4x squared minus 4x minus 16. And in this case, this would be greater than or equal to 0. So the first thing we want to do is find the zeros of this function. So to find the zeros of this function here, of course, we would either come up with a list of possible zeros that work, or we would factor what we have, but definitely if we're finding the zeros, we set it equal to 0. So in this case, I actually notice that if we were to factor this by grouping, okay, -4x minus 16, that this actually indeed works as a factoring method. So we would say x squared comes out of these, I get x plus 4. Over here, we could take out a -4, and I get left with an x plus a 4. And seeing as how these two terms have a common factor of x plus 4, we'll take x plus 4 out in the front here, and we get x squared minus 4, and this is equal to 0. And so at this point, I think that also, while we're at it, let's go ahead and factor this. We get a difference of squares, x plus 2, x minus 2 equal to 0. So one thing I'm going to do is I'm actually going to go back up here underneath our original inequality, and I'm going to write this as the same thing, but it's x plus 4, x plus 2, x minus 2, and we're saying that this is greater than or equal to 0. So in terms of our zeros of this function, okay, our zeros are at x equals -4 and plus or minus 2. So what we want to do is we want to set up our test intervals, and I'm always very keen on drawing a number line here. So in terms of our number line, the x-axis here, we would say that our numbers that are important to us are 1, 2, 3, 4, -5. Our -4 we have a split, okay? At -2 we have a split, and then at +2 we also have a split here. And so our intervals, let's go ahead and talk about our test intervals. Our test intervals occur everywhere in between our indicated zeros, where our function could go from being positive to negative or vice versa. So we're going to set these up, and reading from left to right, it looks like we go -infinity up to -4, -4 to -2, so we would say this is another interval that we have to test for here. From -2 to +2, -2 to +2, and then our last one here would be 2 out to infinity. And so to choose representative x values on each of these intervals, I like to just kind of write these underneath here, and we'll go plug them into our function to see if we get a true or false statement. Between -infinity and -4, -5 works, and it's, not a very big number there, so it's good to choose. Here, -3 would be a good whole number choice. Between -2 and 2, of course we would want to test 0, and between 2 and infinity, 3 is probably like the least of all the evils here. So in terms of testing these out, what we're actually going to do is plug this into our function. Now, do I plug it into the original function, or should I plug it into the factored form? And so what we're going to do is we're going to make a note here. Plug the test values into the factored form of the inequality, And the reason why is because we really just want to ascertain whether or not I get a positive or a negative output on that interval. And so looking at our first test value here, -5, we're going to plug that into this inequality right here. And so we would get -5 plus 4. Okay? We would get -5 plus 2 and -5 minus 2. And so what we're saying here is that this is greater than or equal to 0. So in this case, what I want to point out this time is actually kind of interesting, is that we get a negative here. -5 plus a +2 is a negative here, and -5 minus 2 is a negative here. The bottom line is if you took a negative times a negative times a negative, you would get a negative. And so we would not say that this is a true statement, given that a negative is not greater than or equal to 0 here. And this would be an acceptable statement for me even in my classes. So I would say that this test interval does not pass the original inequality. Now testing x equals -3, we could see that the same thing happens. We just plug this into our function, -3 plus 4, -3 plus 2, and -3 minus 2 is greater than or equal to 0. But this time you see that -3 plus 4 is positive. And -3 minus 2, or plus 2, excuse me, is a negative, and -3 minus 2 is a negative. The interesting thing that happens here is that we get a negative times a negative is a positive, and times another positive is a positive. Basically, we end up with a statement here that passes. And so since this is a true statement, okay, then that means that any x value in this entire interval from -4 to 2 is going to work for us here. So we tested that, and it works. So now plugging in 0, let's try to plug in 0 here. We get 0 plus 4. 0 plus 2, 0 minus 2 is greater than or equal to 0. So we get a positive times a positive times a negative, which is, in this case, negative. And a negative thing is not greater than or equal to 0. So this interval should be lost since it's not satisfying the original inequality. And then the last value here we chose to test was 3. So we would plug 3 into our original inequality here. So we get 3 plus 4, 3 plus 2, 3 minus 2 when we plug those in for x. And so eventually what we end up with is a positive times a positive times a positive. And anytime you do that, you get a positive, which means that we're going to get this true statement here. And this is true. So what this means then is that this last interval is also a solution interval. So let's go ahead and then write our solutions to this, okay? And let's also be very careful of the fact that we had this time a greater than or equal to. So with respect to my intervals here, since we have greater than or equal to, okay, we would have some polynomial function, which by the way just kind of does this little ditty right here. But basically we could see greater than or equal to 0 happens not just above here, but also at these actual zeros here. So in terms of our solutions, we should include -4 and -2. If it helps you, it's because we have a greater than or equal to. Okay? And this is in union with, now, we should also include 2, since 2 is a 0, and our graph would be at a height of 0 there, and then go to infinity on the right, where of course we would not include infinity there. Okay? So the key to these is basically finding your zeros and using those to set up your test intervals, and then we'll just plug in x values in each of those test intervals to see if it satisfies it or not. But if it does satisfy it, then we keep those solutions, being mindful of the fact that it's brackets if it's an or equal to, or parentheses if it's just greater than or just less than. Cheers.